So in this tutorial, we will talk about the conservation of mass. So as we discussed in previous tutorial, we talk about the Reynolds transpose theorem, which we will apply here. So what is the conservation of mass means? It means the mass is conserved in a control volume. It will not change. Whatever the mass is coming in, same mass is going out. For example, this is a control volume. So whatever mass is coming in, same mass is going out. So in and out is equal, and total change in mass in a system is equal to 0. So total change in mass of a system is 0. So let's go to the Reynolds transpose theorem, which we discussed. So total change of a mass in a control volume. So total change in mass system is equal to change in mass per in a control volume. This is control volume, and change of mass over the flux mass over this control surface. So here, so this is again the velocity, and this is unit vector. So the sum of this total mass would equal to 0. So this is now, but this is an integral form. Let's do it for a differential form. So consider a small element. For example, this is, we have delta x, delta y, delta z. So where, let's see, we have a property rho, which is like a density, and we want to see how it will change. So rho dV is a mass. So change of mass is rho dt, because we say rho is uniform in a control volume. Rho is uniform, its density usually fixed for any fluid generally. So rate of change of density for a control volume, so it will be rho dV would be, this will be, is not it is today is not changing, so it's be rho delta x, delta y, delta z. And rate of mass because of the flow, so for is rho u, and let's say in the center is rho, so rho u. So let's go through the Taylor expansion. So for example, let's say in this direction is positive, is negative x direction. So change in mass or convective mass is rho u dd over dx, and at dx by 2. Like for example, this is delta x, so from here to here is delta x by 2. So, or by using the Taylor expansion, rho u d over dx, rho u delta x by 2, and we can neglect the higher order terms. So similar, if we go to the negative x direction, is rho u d delta x, you have a negative direction, d delta x, rho u delta x by 2, and area delta y delta z, the area of this surface, because the second term is for surface area. So this area will be like this, so this area, and then so net mass flow rate in the x direction would be delta x. When you add total mass, so this will cancel, because so it will be in the both directions, so this will cancel out, so this will be add 2 and 2 is cancelled, so total mass, net flow mass would be d delta x, rho u delta x, delta y, delta z. Similarly for other, in y direction, z direction. So now writing on the both side of equation 1 and 2, this is here, I will change like here and here, I will add both, then total I will get d rho dt, and for when we x direction, for y direction, and z direction. So you get a total, so total you will get d rho over dt plus rho d over dx, rho u d over dy of rho v So which is, you can write is as d over dt plus d delta rho v, that is equal to 0. Rho v, this is called divergence. So which is d over dx, d over dy, d over dz. This is called divergence. So this rho, for rho change in density or change of mass per unit time at particular location. So like say then when the flow is steady, there is nothing, nothing is changing. So then the equation, then your total divergence of this will be equal to 0. So you say that would be equal to 0 because there is no change in the density per unit time. For example, if it's a fluid, the fluid or your is incompressible fluid, so then there will be no change in the density per unit time. There will be no change here because of the flow is uncompressible, density doesn't change, so it will be 0 as well, and there is no change in the steadiness, it will be 0. So for incompressible flow, this will be 0. The divergence of velocity is 0. For example, this is, so it will go there, if it go, it will be 0. So the divergence, so this would be important, remember this. It would be useful when you were going for the conservation of momentum and other thing. We would be solving the Navier-Stokes equations. So for incompressible flow, divergence of velocity is 0. Thank you very much. That's all for this video.